Yo guys, so in this video, we will go through everything there is to know about arithmetic, like literally everything, the history, how it works, some theories, and even some predictions for the future. In today's video, I decided to put a video of me working on the video in the background. So yeah, this took a long time to make and I really hope you enjoy. And let's go back to somewhere in what is now the Democratic Republic of Congo. About 20,000 years ago, someone sat down with a small baboon bone and carved notches into it, groupings of 11, 13, 17, 19. Then another row where 3 doubled to 6, 4 doubled to 8, 5 doubled to 10, as if testing a rule. Then another row where every number sat close to a multiple of 10, like it was being pulled towards something it could not quite name. That bone still exists. It is sitting in a glass case at the Royal Belgian Institute of Natural Sciences in Brussels, and nobody fully agrees on what it means. Maybe it was a lunar calendar, maybe it was a counting tool, maybe it was the earliest known multiplication table. Maybe the person who made it was just trying to get a better grip on a handle and scratched some marks in out of boredom. We genuinely do not know. But the marks are not random, and the groupings are not accidental, and the numbers in that bottom row are all the prime numbers between 10 and 20. Whatever was going on in that person's head 20,000 years ago, something was happening that we recognize. A mind was encountering quantity and trying to hold on to it, trying to record it in a world that had no writing, no pen, no paper, no school, no concept of mathematics as a discipline or a subject, or even a word. That tension between the human brain noticing pattern and the human world not yet having a language for it, that is where arithmetic begins. And the whole story of arithmetic is the story of closing that gap over and over across every civilization on Earth for the next 20,000 years. Before we talk about arithmetic as a system, we should talk about what it is built on top of. Because the thing it is built on top of is not paper and it is not clay tablets, it is a brain. Every human alive today, and probably every human who has ever lived, is born with something called number sense. Animals have it too. Crows can distinguish between groups of different sizes. Chimpanzees can track quantities with surprising precision. Rhesus monkeys can order sequences of symbols by magnitude, even without specific training. Even fish, under the right conditions, will choose a group that has more members in it because being in a larger school is safer. The brain does not need school to start caring about quantity. It cares automatically, the way it cares about faces and voices and which direction a threat is coming from. We can hold small quantities in our heads instantly. See 3 objects and you know there are 3 without counting. Psychologists call this subitizing, from the Latin word for sudden. Up to around 4 objects, most people do it without thinking. Past that, something shifts. We start counting. We start using a different part of the brain. We switch from perception to procedure. That switch from seeing a quantity to needing a procedure to determine it is where arithmetic gets its first foothold. Counting is the original arithmetic operation. Everything else grows from it. And counting turns out to be remarkably hard to invent from scratch. The Pirahã people of the Amazon basin, studied extensively by linguist Daniel Everett, have a language with words for roughly 1, 2, and many. Not precise numbers beyond that. Not because they are less intelligent than anyone else, they are not, but because their society has never encountered a situation where precise large-scale counting was necessary for survival. If you do not have that problem, you do not build that tool. Counting beyond small quantities is a technology, and like all technologies, it only appears when something demands it. The Munduruku people of Brazil similarly have only approximate number words. Their language distinguishes between 1, 2, 3, 4, and 5 or more, and experimental work by psychologist Pierre Pica found that Munduruku speakers are perfectly capable of estimating quantities and reasoning about approximate magnitudes. But they do not track exact large numbers with the precision that literate, numerate people in schools develop. This is not a cognitive limitation. It is a reflection of what their environment has and has not demanded from their minds. What all of this suggests is that humans have a rich, intuitive sense of quantity that is biological and ancient. And then, layered on top of that, a precise counting system that is cultural and relatively recent. Arithmetic, the whole formal enterprise, is what happens when you push that second layer as far as it can go. The bone in Brussels is not even the oldest artifact associated with counting. That distinction probably belongs to the Lebombo bone, a small piece of baboon fibula found in the Lebombo Mountains on the border of Swaziland and South Africa, estimated to be about 43,000 years old. It has 29 notches carved into it in what appears to be a deliberate sequence. Some researchers think it was a tally stick. Some think it tracked a lunar cycle, since 29 is close to the length of a lunar month. We cannot be certain. But you have a 43,000-year-old piece of bone that someone deliberately marked, and the marks are not decoration. The problem that started pushing humans toward arithmetic that was more than just tallying was not philosophy, it was grain. Around 12,000 years ago, humans in the Fertile Crescent started doing something nobody had ever done on that scale before: farming. And farming created a problem that foraging never really had. How much do you have? Not approximately, exactly. Because if you store grain for winter and you get the numbers wrong, people die. Because if you trade grain with a neighboring settlement and someone counts differently, you get cheated. Because if you want to divide a harvest among 20 families and you do not have a way of tracking quantities precisely, the whole operation falls apart. The very first recorded use of arithmetic-like symbols comes not from a genius sitting alone thinking about numbers. It comes from bureaucrats, from record keepers, from the people tasked with tracking exactly how much barley went into which warehouse, how many sheep belonged to which shepherd, how many days of labor were owed to which temple. Around 5,000 years ago, in ancient Sumer, which sat in what is now southern Iraq, between the Tigris and Euphrates rivers, the world's first writing system emerged, cuneiform. Wedge-shaped marks pressed into soft clay with a reed stylus, and a huge portion of the earliest surviving cuneiform tablets are not poetry or religion or history. They are accounting records, they are receipts, they are inventories, they are payroll lists for temple workers. One of the oldest readable documents in existence is essentially a receipt for barley. The heading translates roughly to 29,886 measures of barley. Not a prayer, not a poem, a spreadsheet. The historian Duncan Melville put it clearly. The record keepers needed to know not just what came into or left their stores, but how much or how many. That need drove the development of notation that could represent specific quantities, which is to say, That need created written numbers. The Sumerian number system ended up being base 60. Not base 10 like ours. Base 60, meaning the way they grouped numbers and carried values, was organized around 60 rather than 10. Why 60? Nobody is completely certain. The most compelling answer is that 60 has more divisors than any smaller number. It divides cleanly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60 itself. That is 12 divisors. 10, by comparison, has only 4. That difference makes fractions dramatically easier to work with in base 60. A third of 60 is 20. A quarter is 15. A fifth is 12. A sixth is 10. You can divide 60 among almost any reasonable group size and get a whole number, which in a world where division came up constantly was enormously practical. Remnants of that system are still with us right now. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle, 24 hours in a day, which is 2 times 12, itself a highly divisible number that fits within the base 60 framework. These numbers are not arbitrary. They are fossils of a 5,000-year-old number system, so elegantly suited to its purpose that the parts dealing with time and angles survived every subsequent revolution in mathematics. Every time you read a clock or look up a GPS coordinate, you are using arithmetic that descends directly from Sumerian grain counting. The Babylonians, who inherited the Sumerian system 1,000 years later and built on it extensively, took arithmetic further than anyone before them. They built true place value notation, the idea that the position of a digit in a number determines what it represents. The same way the digit 3 means something very different in 30 than it does in 3000. This was a major conceptual leap. It happened in Mesopotamia at least 1,000 years before it happened anywhere else in the world. On clay tablets that have survived 4,000 years, Babylonian scribes calculated square roots to what would be 7 decimal places in our notation. They worked out what we now call the Pythagorean theorem more than 1,000 years before Pythagoras was born. The tablet, known as Plimpton 322, discovered in the early 20th century and now held at Columbia University, contains a table of Pythagorean triples so extensive and so systematically organized that it is clearly the product of a general method, not just a collection of noticed cases. They solved quadratic equations using a method we would recognize as completing the square. They modeled exponential growth, including a problem that essentially asks, if you invest money at 20% annual interest, how many years before it doubles? The answer they calculated was 5 years. It is approximately correct. The Babylonian scribe who pressed that calculation into clay was doing compound interest math 4,000 years ago. And yet this civilization, despite everything it accomplished, had one gaping hole in its number system. It had no zero. When a position in a number was empty, scribes had to infer it from context, the same way you might read 105 from 1 to 5 if someone forgot the middle digit. Later, Babylonian texts developed a placeholder symbol, a specific mark meaning nothing goes here, but it was only ever used in the middle of a number, never at the end. 0 as an actual number, a quantity in its own right, something you could add and subtract and multiply with, was still thousands of years away. That absence mattered more than it might seem. Without 0 as a real number, arithmetic had a ceiling it could not break through. You cannot build a full place value system without a digit that represents nothing. The Babylonians worked around it brilliantly for centuries, but the workaround always carried ambiguity. The real solution required a civilization with a completely different relationship to the concept of nothing. Before we get there, let's go east, because the story of arithmetic was not only being written in the Middle East. China developed its own independent arithmetic tradition, and it was impressively sophisticated. The ancient Chinese used counting rods, physical sticks arranged in patterns on a flat surface to represent numbers, and this system was place value from very early on. Vertical and horizontal orientations of the rods distinguished ones from tens, from hundreds, and the system could represent any number with remarkable efficiency. The mathematical text known as the 9 Chapters on the Mathematical Art, compiled during the Han Dynasty roughly 2,000 years ago and drawing on even earlier material, covers systems of linear equations solved by a method that is essentially Gaussian elimination, fractions, areas and volumes, proportional reasoning, and square and cube roots. The 9 chapters treats negative numbers matter-of-factly. Rules for adding and subtracting them are stated without drama, centuries before European mathematicians would be willing to take them seriously. The Chinese approach was practical and direct. It worked, so they used it. Chinese mathematicians also worked extensively with a technique they called the method of false position, a procedure for solving equations by making a guess, seeing how wrong it is, and adjusting accordingly. This is not a weak or primitive approach. It is a genuinely powerful method and appears independently in Egyptian, Babylonian, and Chinese mathematics, which says something about how naturally the human mind arrives at iterative correction as a problem-solving strategy. The instinct is universal. The notation is what differs. The Mayan civilization, on the other side of the world, from all of these traditions and with no known contact with them, developed its own number system that included a 0. The Mayan system was base 20, probably because humans have 20 fingers and toes, and within that structure they used positional notation with a shell-shaped symbol for 0. The Maya used this system primarily for calendrical calculations, and they built astronomical records of extraordinary precision. Their calculation of the length of the year was more accurate than the Julian calendar that Europeans were using centuries later. All of that precision required arithmetic, and their arithmetic had 0. The independent invention of 0 in both India and Mesoamerica suggests that once you build a positional number system sophisticated enough, 0 becomes something you feel the absence of. Both civilizations arrived at the same solution from different directions. The difference was in what happened next. The Indian 0 spread, transformed arithmetic globally, and changed the world. The Mayan 0 stayed in Mesoamerica, and the civilization that built it was destroyed before its mathematical tradition could travel. The history of arithmetic is partly the history of which ideas got carried and which got buried. The Egyptians arrived at arithmetic from yet another direction, with yet another set of priorities, and ended up with a fascinatingly distinct system. Ancient Egyptian math, documented most thoroughly in the Rhind mathematical papyrus from around 1650 BCE and the Moscow mathematical papyrus from roughly the same era, was deeply practical and impressively sophisticated in certain narrow areas. Egyptians were obsessed with fractions, specifically with unit fractions, meaning fractions with 1 in the numerator, a half, a third, a quarter, an eighth. They expressed almost every fractional quantity as a sum of these unit fractions, which sounds limiting but actually works for most real-world quantities and sometimes produces results that are more computationally convenient than the way we would express the same thing today. For multiplication, Egyptian scribes used a method of repeated doubling. To multiply 7 by 13, they would build a table. 1 times 13 is 13, 2 times 13 is 26, 4 times 13 is 52. Then they would express 7 as 1 plus 2 plus 4, add the corresponding rows, and get 91. The process works for any multiplication regardless of how large the numbers get, and it requires only doubling and addition. A scribe with a good memory can do it reliably without error. Interestingly, this is very close to how computers perform multiplication at the hardware level. The binary representation of a number is essentially a record of which powers of 2 to add together, and multiplying in binary is exactly the kind of doubling and adding that Egyptian scribes were doing by hand thousands of years earlier. The Moscow mathematical papyrus contained something remarkable: a correct formula for the volume of a truncated pyramid, a frustum, where you cut off the top and are left with a shape that is wide at the base and narrower at the top. The formula requires knowing the side lengths of the top and bottom faces and the height, and combining them in a specific way that involves a squared term. The result is not approximate, it is exact. How Egyptian mathematicians arrived at this result, whether through physical measurement and clever induction or through something resembling a geometric proof, is not recorded and remains a genuine historical mystery. Both Egypt and Babylon were doing arithmetic for thousands of years, but neither of them was asking the question that would produce the next major transformation. The Greeks changed everything by asking, what is this actually? Not how do we use numbers, but what are numbers? Not how do we compute, but why do these rules hold? The shift from arithmetic as a practical tool to arithmetic as an object of investigation that happened in ancient Greece starting around the 6th century BCE, and it changed what mathematics was capable of forever. Pythagoras, who lived around 570 to 495 BCE, and his followers became obsessed with the idea that numbers were the deep structure of reality, not metaphorically. Literally, they believed that number explained music. They were not wrong. The relationships between musical notes are genuinely ratios of whole numbers. A string vibrating at twice the frequency of another produces a tone an octave higher, and a ratio of 3 to 2 produces a perfect fifth. The Pythagoreans noticed this, experimented with it, and concluded that numerical ratio was the organizing principle of the cosmos. They organized themselves around mathematical study in a way that looked less like a school and more like a religious community. Then they made a discovery that nearly shattered their worldview. The square root of 2, the length of the diagonal of a square with sides of length 1, cannot be expressed as a ratio of whole numbers. It goes on forever without repeating. It is not rational. The Pythagoreans, whose entire philosophy depended on numbers being whole and orderly and expressible as ratios, reportedly had enormous difficulty accepting this. The story, possibly legend, says that a man named Hippasus proved the irrationality of the square root of 2 and was thrown overboard from a ship by his fellow Pythagoreans, who could not tolerate the implication. Whether that is history or mythology, the mathematical crisis was real. Here was a quantity that clearly existed, that you could draw with a ruler and compass, and that clearly could not be expressed within the number system they had. Then there was Euclid. Euclid, working around 300 BCE in Alexandria, wrote a book called Elements that is probably the most influential mathematics textbook in history. It was used in schools for over 2,000 years. Abraham Lincoln reportedly taught himself logical reasoning by reading it. It codified not just specific mathematical results, but the entire approach of starting from clear premises and deriving everything else through careful logical argument. Within its pages, among many other things, Euclid proved that there are infinitely many prime numbers. The proof is so elegant that it still shows up in undergraduate textbooks today. Assume the list of prime numbers is finite. Multiply all of them together and add 1. The resulting number is either prime itself, which means it was not on your supposedly complete list, or it has a prime factor that is also not on your list, because dividing any prime on your list into this new number always leaves a remainder of 1. Either way, you have found a prime that was not in your supposedly complete collection. The assumption that the list is finite leads to a contradiction. Therefore, the list is infinite. That argument was constructed around 300 BCE. No one has ever found a flaw in it. Eratosthenes of Cyrene, working in Alexandria around the same era, developed a method for finding all prime numbers up to any given limit that is still taught today. Write out all the numbers, starting from 2. 2 is prime, so circle it and cross out every multiple of 2. 3 is prime. Circle it and cross out every multiple of 3. The next uncrossed number is 5. Circle it and cross out its multiples. Keep going. Whatever is left uncrossed after you have eliminated all multiples of all primes up to the square root of your limit is prime. This is the sieve of Eratosthenes, and it is a beautiful piece of arithmetic reasoning, a procedure that exploits the multiplicative structure of the integers to reveal the primes by elimination. Eratosthenes also calculated the circumference of the Earth using arithmetic and geometry by measuring the angle of the sun's shadow in 2 different cities at the same time of year, and using proportional reasoning to scale up from the distance between the cities to the full circumference. His answer was about 40,000 kilometers. The actual circumference of the Earth is about 40,075 kilometers. He was off by less than 1%. He used nothing but a stick, a shadow, and arithmetic. Diophantine of Alexandria, working around the 3rd century CE, pushed arithmetic in a direction that had never been explored before. He asked not just what a number was, but what kind of number satisfied a given equation. His Arithmetica posed problems like, find 2 numbers whose sum is a given number and whose product is a given number. Find the right triangle whose sides are rational numbers. Find 3 numbers such that the product of any 2 plus the sum of those 2 equals a given number. These are arithmetic questions with an algebraic flavor. Diophantine was asking about the structure of solutions rather than just computing specific answers. The problems in Arithmetica were so rich that a 17th century French mathematician named Pierre de Fermat, reading a copy of the text one evening, was inspired to write a note in the margin. He had found, he claimed, a remarkable proof of something that Diophantus's work brought to mind. That marginal note became the most famous unproven claim in the history of mathematics. We will come back to it. The Greeks also gave us the word that names this subject, arithmetic, from arithmos, meaning number. For the Greeks, Arithmetic referred specifically to the theoretical study of number, not practical calculation, which they called logistic. The distinction between counting as a tool and counting as a subject of inquiry, that is a Greek contribution, and it set the stage for everything that followed. What the Greeks did not contribute, despite all their sophistication, was a good number notation. They used letters of their alphabet to represent numbers, a system that made arithmetic operations genuinely cumbersome. Trying to do long multiplication in the Greek alphabetic system is a painful exercise. And the Romans, who dominated the Mediterranean world for centuries after the Greeks, had an even worse system for calculation. Roman numerals are fine for recording fixed quantities, but terrible for computation. Multiplying MML x x x IV by MCD XCII is essentially impossible without converting to something else first. The Mediterranean world had the theory of numbers worked out to an impressive degree, but it was still waiting for a notation that would make everyday computation fast and reliable. That notation was being developed on the other side of the world. India, in the 5th and 7th centuries, CE produced what might be the single most consequential contribution to arithmetic in all of human history: zero. Not zero as a placeholder, not zero as an empty position in a number, zero as an actual number, a quantity, something you can add to other things, subtract from other things, multiply with other things. A number that answers the question, what is the result of taking a number and removing it from itself entirely? This sounds simple. It was not. Civilizations that had been doing sophisticated mathematics for thousands of years had not managed it. The Babylonians had a placeholder. The Maya had a placeholder. But a placeholder is just a symbol that says nothing goes here. It is not yet a number. Making zero a number requires treating nothing as a thing, and that requires a specific philosophical willingness to say that the absence of quantity is itself a quantity. The Indian mathematical tradition had that willingness, and it almost certainly came from somewhere unexpected: philosophy and spirituality. Hindu and Buddhist thought had long engaged with the concept of shunyata, emptiness, void, nothingness, as a real and serious metaphysical concept, not as an absence or deficiency, but as a genuine state of being. The Sanskrit word shunya, meaning empty, is the direct ancestor of our word zero by way of the Arabic sifr, meaning empty, which became the Latin zephyrum, which eventually became zero. The philosophical groundwork for treating nothing as something was already laid when the mathematicians arrived at the problem. Aryabhata, working in the 5th century CE, introduced a place value decimal system that implicitly required a zero. You cannot have position-dependent values without a way to mark an empty position. He calculated pi to 4 decimal places, a remarkable achievement, and produced astronomical tables of high accuracy. But it was Brahmagupta, writing in 628 CE, who formalized zero as a full arithmetic entity. His work, the Brahmasfuta Siddhanta, stated the rules clearly. A number plus zero is that number. A number minus zero is that number. A number times zero is zero. Zero times zero is zero. Brahmagupta got one thing wrong. He said 0 divided by 0 equals 0, which is not right. Division by 0 turns out to be undefined, and the reasons why are genuinely interesting. Dividing 10 by 5 means asking how many 5s fit into 10, and the answer is 2. Dividing 10 by 0 means asking how many zeros fit into 10. You can fit 0 into any number infinitely many times, or you can argue it fits 0 times, or you can argue the question has no consistent answer. Different framings lead to different conclusions. Whenever a question has no consistent answer, mathematics says it is undefined. That is not a failure. It is a boundary marker. Brahmagupta tried to assign an answer and got it wrong, but his instinct to make arithmetic complete, to ensure every operation had a result, was correct. The specific answer was wrong. The direction was right. On everything else, he had it. 0 was a number, and that single addition to the number line changed what arithmetic could do. Combined with place value notation, 0 made it possible to write any number at all using just 10 symbols. You can express 1 and 1 billion and 10 trillion using the same 10 digits, just arranged differently. The system is so efficient and so flexible that when people today talk about Arabic numerals, what they are really talking about is the Indian system transmitted through the Arabic world, and the deepest innovation in that system is the Indian decision that 0 is a number. The decimal system with 0 also made arithmetic operations dramatically faster. Addition and subtraction with place value notation are straightforward mechanical processes. Multiplication becomes long multiplication, still effortful but systematic. Division becomes long division. You do not need to convert between systems or rely on lookup tables. The algorithm for calculating with numbers is the same for large numbers as for small ones, just with more steps. An algorithm, that word is about to become central. The bridge between the Indian system and the world as we know it today was built by a Persian scholar working in Baghdad in the early 900 CE. His name was Muhammad ibn Musa Al-Khwarizmi, and his contribution to arithmetic is so profound that his name survives in the English language in distorted form every single time someone says the word algorithm. Al-Khwarizmi worked at the House of Wisdom in Baghdad, an institution funded by the Abbasid Caliphate that collected and translated scholarly works from Greek, Indian, Persian, and other traditions. It was one of the great intellectual projects in human history, a systematic effort to gather and synthesize the accumulated knowledge of multiple civilizations. Al-Khwarizmi synthesized the Indian decimal number system with place value notation and 0, and wrote a treatise called On the Calculation with Hindu Numerals. When that treatise was later translated into Latin, the translators rendered his name as Algorithmi, and the word for his computational method became algorithm, and eventually algorithm. Al-Khwarizmi also wrote a second foundational work on solving equations, whose title in Arabic was Al-Kitab al-Mukhtasar fi Hisab al-Jabr wal-Muqabala. The word al-Jabr in that title, referring to one of the two operations he used to manipulate equations, became the word algebra. One person's name gave us the word algorithm. One word from one of his book titles gave us the word algebra. Few mathematicians have had a more direct impact on the vocabulary we use to think about mathematics. Al-Khwarizmi was not just translating Indian mathematics, he was demonstrating it. He showed step by step how to perform addition, subtraction, multiplication, and division using the Hindu-Arabic system. And he showed how much simpler these operations were compared to any system Europe or the Middle East had been using. His work made a direct case. This is better use this. The decimal system spread west through the Islamic world and into Europe, arriving through Spain and southern Italy during the 12th and 13th centuries. A community of scholars in Europe began advocating for the Hindu-Arabic system under the name algorists, after Al-Khwarizmi's Latinized name. They faced real resistance from abacists, people who used the abacus and Roman numerals and had been doing so reliably for centuries. The debate was occasionally heated. There are records of city governments in medieval Europe actually banning the use of Hindu-Arabic numerals in commercial transactions, partly out of concern that the unfamiliar symbols could be forged or altered more easily than Roman numerals. The abacus deserves more attention than it usually gets. The word comes from the Greek abax, meaning flat surface, and the tool in its various forms was one of the primary computational instruments of the ancient and medieval world. The Chinese suanpan, the Japanese soroban, the Roman hand abacus, the Russian skoti, all variations on the same idea, a physical device that externalizes the process of carrying and borrowing in arithmetic. A skilled abacus operator can perform addition, subtraction, multiplication, and division at speeds that rival or exceed a person doing the same operations on paper. Before electronic calculators, competitions between abacus operators and arithmetic on paper practitioners produced results that surprised audiences expecting the pencil and paper method to win. The abacus works because it makes place value physical. Each column of beads represents a position: ones, tens, hundreds, thousands. Carrying a 10 from the ones column to the tens column is a physical gesture, moving beads from one row to another. The cognitive load of tracking the carry is offloaded onto the physical structure of the device. You can make arithmetic easier by building a tool that matches the architecture of the number system. The abacus was that tool for thousands of years, and in parts of the world it still is. Then came Fibonacci. Leonardo of Pisa, known as Fibonacci, published the Liber Abaci in 1202. This book introduced the Hindu-Arabic numeral system to Europe with enormous practical detail. Here is how to do business arithmetic with these numbers. Here is how to calculate interest. Here is how to convert currencies. Here is how to work out profits on trade. Fibonacci was a merchant's son who had grown up in North Africa and seen firsthand how much faster commerce moved when you used the decimal system. His book was aimed at merchants and traders, and it worked. Over the next few centuries, the Hindu-Arabic system gradually displaced Roman numerals across Europe for calculation. The resistance was real. Roman numerals had been in use for 1,000 years. Banks and merchants had systems built around them. There was also suspicion of anything connected to Islamic scholarship. It took centuries. But by the 1600s, Roman numerals in calculation contexts had essentially vanished, replaced by a number system invented in India, transmitted through Persia and the Arabic world, and introduced to Europe by an Italian merchant's son who saw the practical advantage. One more invention belongs in this section of the story because it changed how people worked with arithmetic for 2 centuries and deserves to not be forgotten: logarithms. In 1614, the Scottish mathematician John Napier published a table of logarithms, a concept he had spent 20 years developing. The basic idea is this: multiplication is hard, but addition is easy. If you could convert multiplication problems into addition problems, you could make calculation dramatically faster. Logarithms do exactly that. The logarithm of a number is the exponent you would need to raise a fixed base to in order to get that number. The logarithm base 10 of 1000 is 3 because 10 to the power of 3 is 1000. The key property of logarithms is that the logarithm of a product equals the sum of the logarithms. So to multiply two large numbers, you look up their logarithms in a table, add the logarithms together, and then look up which number corresponds to the result. This might sound like an indirect route, and it is. But before electronic calculators, it was dramatically faster than performing large multiplications by hand. Astronomers, navigators, engineers, and scientists used logarithm tables for 3 centuries. The slide rule, which performs multiplication and division by mechanically adding and subtracting logarithmic scales, was the pocket calculator of the pre-electronic age. Napier's invention reduced the time required for certain astronomical calculations from hours to minutes. Edmund Gunther, a contemporary of Napier, noted that the logarithms had saved many a man's life. He was talking about navigators who needed to compute positions quickly at sea. Arithmetic, through logarithms, was literally saving people from shipwreck. So now the world has a number system that works. 10 digits, 0 through 9, positional notation, and a set of operations that can be performed on any pair of numbers using systematic procedures. The question becomes, what actually are these operations and why do they work the way they do? Addition is the operation of combining quantities. When you have 3 apples and someone gives you 4 more, you have 7. The reason addition gives a single definite answer is that quantity is consistent. There is an actual fact about how many apples are in a pile, and combining 2 piles always produces a specific third quantity. Addition does not need to be justified philosophically. It is the most direct translation of physical reality into mathematics. What makes addition mathematically interesting is the properties it has that we take completely for granted. Order does not matter. 3 plus 4 equals 4 plus 3. This is called commutativity, and while it seems obvious for addition, it is not obvious for all operations. Subtraction is not commutative. 3 minus 4 is not the same as 4 minus 3. Commutativity is a specific feature of addition, not a universal truth about operations in general. Grouping does not matter either. 2 plus 3 plus 4 gives the same result whether you add 2 and 3 first and then add 4, or add 3 and 4 first and then add 2. This is associativity. Again, it seems natural for addition, but fails for subtraction. These properties are why arithmetic with addition has a clean, reliable, predictable structure that can be extended to larger and larger calculations without things breaking down. The identity element of addition is 0. Adding 0 to anything gives you back the same thing unchanged. This is exactly why 0 as a number matters so much. It completes addition. Every number has an additive inverse, a number you can add to it to get back to 0. The additive inverse of 5 is -5. This is where negative numbers enter the picture and where many people in history had trouble. Negative numbers are conceptually strange. They represent quantities below 0. In a world of counting physical objects, they do not make immediate intuitive sense. You cannot have -3 apples. Early mathematicians in Europe and even in parts of the Indian tradition resisted negative numbers as absurd or fictitious. Brahmagupta worked with them. Al-Khwarizmi largely avoided them. Blaise Pascal and René Descartes, two of the sharpest thinkers of the 17th century, were still skeptical about whether negative numbers were fully coherent. The resistance makes sense. Negative numbers require you to extend your imagination beyond the physical world of counting into a more abstract space where numbers represent positions or differences or debts rather than quantities of objects. The number line, which we teach children early and take for granted, is actually a conceptual achievement of a high order. It requires imagining zero as a point, positive numbers extending in one direction forever, negative numbers extending in the other direction forever, and every real number existing somewhere on that infinite line. That is not a natural or obvious representation. It took thousands of years of accumulated thought to arrive at it. It required the philosophical willingness to say that nothing is a place, that debts are numbers, that what you do not have is as numerical as what you do have. Subtraction is addition in reverse. Subtracting 4 from 7 is the same as adding -4 to 7. This is why subtraction undoes addition. They are inverse operations. That inverse relationship, the way operations pair up to cancel each other out, runs through all of arithmetic and turns out to be much more important than it first appears. If you know that something plus 3 equals 7, you can subtract 3 from both sides and find the something. The ability to undo operations is what makes arithmetic a tool for discovering unknown quantities, not just combining known ones. Multiplication is where arithmetic starts to get genuinely interesting in terms of structure. At its most basic level, multiplication is repeated addition. 5 times 3 is 3 added to itself 5 times. 3 plus 3 plus 3 plus 3 plus 3 equals 15. That is a completely valid way to think about it, and it is how multiplication is usually introduced. But that framing breaks down quickly when you try to extend it. What does it mean to add 3 to itself 1/2 times? What does it mean to add something to itself -2 times? Multiplication is ultimately something more general, something about scaling, about rates, about how quantities combine when one of them is a factor of the other. Multiplication is commutative, like addition. 5 times 3 equals 3 times 5. This is not immediately obvious from the repeated addition framing. Why should adding 3 5 times give the same result as adding 5 3 times? But the geometric reason is clear if you imagine a 5 by 3 grid of dots. Counting the rows gives you 3 groups of 5. Counting the columns gives you 5 groups of 3. Same number of dots either way. The grid makes the commutativity visual and undeniable. Multiplication distributes over addition. 2 times the sum of 3 and 4 equals 2 times 3 plus 2 times 4. This is the distributive property, and it is the engine behind most of algebra and a huge part of arithmetic. The reason long multiplication works at all is the distributive property. When you multiply 234 by 56, you are really multiplying 234 by 50 and adding that to 234 times 6, because 56 is 50 plus 6. Each of those can be decomposed again. The whole procedure unwinds into additions of simple products because multiplication distributes over addition. Without that property, no shortcut method of multiplication would work. The identity element of multiplication is 1. Multiplying anything by 1 leaves it unchanged. Every number except 0 has a multiplicative inverse, a number you can multiply by to get back to 1. The multiplicative inverse of 5 is 1/5. Multiplying 5 by 1/5 gives 1, just as adding 5 to -5 gives 0. The inverse structure of multiplication mirrors the inverse structure of addition, and this parallel structure is one of the deepest features of arithmetic. 0 times anything is 0. This follows from the distributive property. Write 0 as 0 plus 0. Distribute some number n over that sum, and you get n times 0 plus n times 0 equals n times 0. The only way this is consistent is if n times 0 equals 0. It is forced. It is not a rule someone decided to make up. It is a consequence of how multiplication interacts with addition. This also explains why division by 0 does not work. Division is the inverse of multiplication. Dividing a number by 0 should give a number you can multiply by 0 to get back to the original. But anything times 0 is 0. There is no number you can multiply by 0 to get 5. Division by 0 has no consistent answer, so it is not an operation you can perform. Division is to multiplication what subtraction is to addition, the inverse operation. Dividing 12 by 4 is asking, what number multiplied by 4 gives 12? The answer is 3. Division undoes multiplication, but division does not always produce a whole number. Dividing 7 by 2 gives 3.5. Dividing 1 by 3 gives a number that does not terminate when written in decimal. 0.3, 3, 3, 3, and on forever. These results require extending the number system beyond whole numbers, and that extension leads to fractions. A fraction is a ratio, part of something relative to a whole. 2/3 means 2 parts out of 3 equal parts. Fractions are how arithmetic handles division that does not come out evenly, and they come with their own rules that can trip people up precisely because they do not feel like the rules for whole numbers. Adding fractions with the same denominator is easy. 2/3 plus 1/3 equals 3/3, which equals 1. You are just adding the numerators. But adding fractions with different denominators requires finding a common denominator first. 2/3 plus 1/2 requires converting both to sixths. 4/6 plus 3/6 equals 7/6. The reason you need a common denominator is that you cannot meaningfully combine parts of different sizes. Adding thirds to halves without first converting them is like adding meters to feet and calling the answer a length. You need a common unit. Multiplying fractions is counterintuitively simpler than adding them. 2/3 times 3/4 is just 2 times 3 over 3 times 4, which is 6/12, which simplifies to 1/2. You multiply the numerators and multiply the denominators. Dividing fractions is multiplying by the reciprocal. Dividing by 2/3 is the same as multiplying by 3/2. The reason this works is that dividing by a fraction asks how many of that fraction fit into the number you started with, and the answer to that has the same structure as multiplication by the reciprocal. When you multiply 2/3 by 3/4, you are taking 2/3 of something that is already only 3/4 of something else. The result is smaller than either factor. That is why multiplying two numbers that are both less than 1 gives a result smaller than both. It surprises people when they first encounter it, because we are used to multiplication making things bigger. Multiplication makes things bigger when the multiplier is greater than 1. When the multiplier is less than 1, it scales down. The rule is not different, the direction of the scaling is. Fractions open up the entire space between the whole numbers, between 0 and 1, between 1 and 2, between any two consecutive whole numbers. There are infinitely many fractions. Between 999 thousandths and 1 there are infinitely many. The number line is not made of dots spaced out along a line, but of something continuous and dense, where every interval contains more numbers than you could ever count. But fractions do not cover everything. The Pythagoreans found that out to their discomfort. The square root of 2 cannot be written as a fraction. The proof is beautiful and brief. Suppose the square root of 2 equals p over q, a fraction in lowest terms where p and q share no common factors. Then p squared equals 2q squared. That means p squared is even, which means p itself is even. Write p as 2 times some number m. Then 4m squared equals 2q squared, which simplifies to q squared equals 2m squared, which means q squared is even, which means q is even. But we said the fraction was in lowest terms, so p and q cannot both be even. Contradiction. The square root of 2 cannot be written as a fraction. There are infinitely many irrational numbers. In fact, there are, in a precise mathematical sense, more irrational numbers than rational ones, even though there are already infinitely many rationals. This is one of the weirder results in the theory of infinity, worked out by Georg Cantor in the 1800s. Cantor proved that you cannot list all the real numbers. You can try to match them one-to-one with the counting numbers, and no matter how carefully you arrange your list, you can always produce a real number that is not on it. The rational numbers, by contrast, can be listed. So, in a precise technical sense, there are more irrationals than rationals, more reals than rationals, even though all three sets are infinite. This was not easy for Cantor's contemporaries to accept. The great mathematician Henri Poincaré called Cantor's work a disease from which mathematics would eventually recover. Leopold Kronecker reportedly called Cantor a corrupter of youth. The resistance was visceral. The idea that infinity had sizes, that some infinities were bigger than others, cut against deep intuitions about what infinity was. Cantor had nervous breakdowns. He spent time in sanatoriums. He died in poverty in a mental institution in 1918. His work is now recognized as one of the deepest achievements in the history of mathematics, and the theory of different sizes of infinity is taught in standard undergraduate courses. The most famous irrational numbers have names. Pi, the ratio of a circle's circumference to its diameter, is irrational, which means it never ends and never repeats when written in decimal. It goes 3.1415926535897993 23846264264 338327950288419711693 939375945949592306408628628620899862086. 8 0 3 4 8 2 5 3 4 2 1 1 7 0 6 7 9 8 2 1 4 8 0 8 6 5 1 3 2 8 2 3, and it keeps going. Pi has been calculated to over 100 trillion decimal places and shows no signs of ending or repeating because it cannot. Pi is also transcendental, which is a stronger condition than irrational. A transcendental number is one that is not the root of any polynomial equation with rational number coefficients. The square root of 2 is irrational but not transcendental. It satisfies the equation x squared minus 2 equals 0. Pi satisfies no such equation. The proof that pi is transcendental, completed by Ferdinand von Lindemann in 1882, immediately settled a 2,000-year-old problem. The ancient question of squaring the circle, constructing a square with the same area as a given circle, using only a ruler and compass, is impossible. The impossibility is a direct consequence of pi being transcendental. The number e, Euler's number, approximately 2.71828, is also transcendental and irrational. It arises in compound interest, population growth, radioactive decay, the shape of a hanging chain, the distribution of prime numbers. It can be defined as the limit of the sequence produced by taking 1 plus 1 over n raised to the power of n as n gets arbitrarily large. It can also be defined as the sum of the infinite series 1 plus 1 plus 1/2 plus 1/6 plus 1/24 and so on, where each term is 1 divided by the factorial of its position. All of these definitions give the same number. That convergence of completely different looking formulas onto the same constant is one of the things that makes you feel like it is being discovered rather than invented. Real numbers, the rationals together with the irrationals, filled the number line completely. There are no gaps. Between any two real numbers, no matter how close, there is another real number. The number line is a continuum. This is the space in which arithmetic operates. Now let's look at the deeper architecture of that space. The whole numbers 1, 2, 3, 4, and so on are called the natural numbers, and they have been the subject of mathematical study for as long as mathematics has existed. Within the natural numbers, there is a hierarchy. Some numbers can be broken into smaller factors, and some cannot. The ones that cannot, the numbers divisible only by 1 and themselves, are the prime numbers. 2 is prime, 3 is prime, 4 is not prime, it is 2 times 2, 5 is prime, 6 is 2 times 3, 7 is prime, 8 is 2 times 2 times 2, 9 is 3 times 3, 10 is 2 times 5, 11 is prime, 12 is 2 times 2 times 3. The prime numbers 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71. They keep going forever, as Euclid proved. Primes are, in a precise sense, the atoms of arithmetic. Every whole number greater than 1 is either a prime or a product of primes, and that factorization is unique. 12 is always 2 times 2 times 3, no matter what order you write the factors in. 100 is always 2 times 2 times 5 times 5. 630 is always 2 times 3 times 3 times 5 times 7. This result that every integer has a unique prime factorization is called the fundamental theorem of arithmetic, and it is the bedrock of number theory. The uniqueness part matters as much as the existence part. It would be possible to imagine a universe where some numbers had multiple different prime factorizations. In our arithmetic, that does not happen. The prime factorization is unique, and that uniqueness is what gives the primes their power as building blocks. You can always decompose any integer into its prime components and know that the decomposition is the only one. The distribution of prime numbers through the integers is one of the great mysteries of mathematics. They thin out as numbers get larger. The gaps between consecutive primes grow on average as you move further up the number line, but they never disappear entirely. The prime number theorem, proved independently by Jacques Hadamard and Charles de la Vallée-Poussin in 1896, says that the number of primes up to any given value, n, is approximately n divided by the natural logarithm of n. This is a precise statement about how primes are distributed on average, and it was one of the great triumphs of 19th century mathematics. But it says nothing about the fine structure, where exactly each prime sits, how large the gaps can get, whether certain patterns persist. Every now and then, even in the vast reaches of the number line where primes are sparse, you find two primes just two apart, 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31, 41 and 43. These are called twin primes. Nobody knows if they go on forever. The twin prime conjecture says yes, but after more than a century of effort, no one has proved it. In 2013, the mathematician Yitang Zhang proved something that represented genuine progress on the twin prime problem, though it fell short of the full conjecture. He showed that there are infinitely many pairs of primes that differ by at most 70 million. 70 million is a lot larger than 2, but before Zhang's result, no finite bound was known at all. Subsequent work by James Maynard and others in a collaborative mathematical project called Polymath 8 brought the bound down to 246. The bound has to reach 2 for the full twin prime conjecture to be settled. Getting from 70 million to 246 in a year was extraordinary. Getting from 246 to 2 may require something entirely new. Goldbach's conjecture, proposed by Christian Goldbach in a letter to Leonhard Euler in 1742, says that every even number greater than 2 can be written as the sum of two prime numbers. 4 equals 2 plus 2, 6 equals 3 plus 3, 8 equals 3 plus 5, 10 equals 5 plus 5, 12 equals 5 plus 7, 100 equals 3 plus 97, or 11 plus 89, or 17 plus 83, or 29 plus 71, or 41 plus 59, or 47 plus 53. This has been checked for every even number up to 4 quintillion, and it always works. But it has never been proved for all even numbers, and despite nearly 300 years of attempts, it remains unproven. Fermat's last theorem, the claim Fermat scrawled in the margin of his copy of Diophantine, is the most famous case of a conjecture that seemed obviously true and took an extraordinarily long time to prove. Fermat claimed in 1637 that there are no positive whole number solutions to the equation x to the n plus y to the n equals z to the n for any n greater than 2. For n equals 2, there are infinitely many solutions. 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. But for any higher power, Fermat claimed no solutions exist, and he wrote that he had found a remarkable proof that the margin was too narrow to contain. The margin was always too narrow. Mathematicians attacked the problem for 3.5 centuries. Special cases were proved, the case of n equals 3 by Euler, n equals 5 by Dirichlet and Legendre, n equals 7 by Lamé. But the general case remained open. Then, in 1995, after 7 years of secret work, the British mathematician Andrew Wiles published a proof. It ran to over 100 pages. It required tools from areas of mathematics that did not exist when Fermat wrote his note. Whether Fermat had actually found a proof using only the mathematics of his era is essentially impossible to believe. The most probable explanation is that he made an error and never noticed. But his claim drove 3.5 centuries of mathematical development, and the territory it opened up transformed number theory entirely. These open conjectures, clean and simple to state but impossible to verify for all cases, reveal something important about primes. They follow the rules of arithmetic exactly, generated by a completely deterministic process, and yet their distribution looks random. There is no formula that takes an integer and tells you whether it is prime faster than just checking. There is no pattern in where they appear that would let you predict the next one. They are the product of pure arithmetic, and they behave as if someone scattered them randomly along the number line. This mystery is the beating heart of number theory, and at its center sits what is probably the most famous unsolved problem in all of mathematics. In 1859, Bernard Riemann published a single 8-page paper, his only contribution to number theory, that proposed a connection between the distribution of prime numbers and a function defined over the complex numbers. The function is the Riemann zeta function, and the connection he proposed has completely resisted proof for more than 160 years. The zeta function, in its simplest form, is an infinite sum, 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, and so on, where s is a complex number. A complex number has a real part and an imaginary part, extending the number line into a two-dimensional plane. Riemann showed that the zeta function, extended properly to the whole complex plane, contains infinitely many points where it equals 0, and these zeros carry information about how primes are distributed. The Riemann hypothesis says that all the non-trivial zeros of the zeta function lie on a specific vertical line in the complex plane, the line where the real part equals 1/2. If it is true, then the prime numbers are distributed as evenly as they possibly could be, given that they must thin out on average. The errors in any estimate of how many primes exist up to some value n are bounded in the tightest way. They cannot cluster or clump more than a certain amount. Every mathematician who has thought about this problem seriously believes the Riemann hypothesis is true. Computers have checked more than 10 trillion zeros of the zeta function. Every single one lies on the critical line. Not a single counterexample has ever been found, and yet the proof eludes everyone. Entire careers have been dedicated to it. David Hilbert, who in 1900 laid out a list of the 23 most important unsolved problems in mathematics, put the Riemann hypothesis on the list. The Clay Mathematics Institute in 2000 offered a $1 million prize for its proof. It remains unclaimed. What makes the Riemann hypothesis especially haunting is how it connects two things that seem like they should have nothing to do with each other. On one side, the integers, the counting numbers, generated by the simplest possible rule. On the other side, the complex plane, an abstract two-dimensional space where analysis and function theory live. The zeta function throws a bridge between these two worlds and says that the pattern of zeros in the complex plane encodes the distribution of primes on the real number line. That a fact about where a complex valued function equals 0 should determine where the atomic units of multiplication appear among the integers is the kind of deep structural connection that makes mathematics feel like exploration rather than invention. Now, let's move from the abstract to the concrete, because arithmetic is not only a theoretical enterprise, it is infrastructure. It is the thing underneath almost every technology you interact with and every system you rely on. Start with commerce, because that is where arithmetic started. Every financial transaction in human history has been an arithmetic operation. Buying and selling required addition and subtraction long before money was invented, and the development of arithmetic was largely driven by commercial need. The Babylonian clay tablets calculating interest on loans, that was arithmetic serving commerce 4,000 years ago. The Egyptian papyri calculating how to divide rations among workers, arithmetic serving administration. Fibonacci's Liber Abaci, which introduced the decimal system to Europe, was explicitly and primarily a book about commercial arithmetic. Double-entry bookkeeping, formalized by Luca Pacioli in 1494, is a direct application of the additive structure of arithmetic. The fundamental idea is that every transaction affects two accounts, and the sum of all debits must equal the sum of all credits at all times. If you buy inventory, your assets account goes up and your cash account goes down by the same amount. The balance is maintained by arithmetic. Errors show up as arithmetic inconsistencies. Fraud, historically, has often been detectable because fraudulent entries break the arithmetic balance. The system does not require trust. It requires correct arithmetic, and incorrect arithmetic reveals itself. Modern financial systems are arithmetic at a scale that is genuinely difficult to comprehend. The New York Stock Exchange processes on the order of 1 billion messages per day. Every trade, every bid, every ask, every price update is arithmetic. High-frequency trading firms run arithmetic algorithms that make thousands of decisions per second, reacting to price changes in microseconds. The pricing of derivatives, financial instruments whose value depends on other assets, requires solving differential equations numerically, which is arithmetic. The capital requirements that banks must hold to remain solvent are calculated by arithmetic models of risk. The global economy is, at a computational level, an enormous arithmetic calculation running continuously. Navigation brought arithmetic into the physical world of motion and position. The problem of determining where you are when you are in the middle of an ocean with no landmarks has driven some of the most sophisticated practical arithmetic in history. That reckoning, estimating your current position from your last known position, your speed, your direction, and the time elapsed, is arithmetic. Multiply speed by time to get distance. Use trigonometry to project that distance in the direction of travel. Add it to your starting coordinates. It works perfectly if your measurements are perfect. In the real world, errors accumulate, which is why sailors needed additional methods. Celestial navigation uses the angles of known stars above the horizon to determine position. The angle of the sun at solar noon tells you your latitude directly. Longitude requires knowing the exact time at a reference meridian compared to your local solar noon. which is why the British government offered a £20,000 prize in 1714 for a reliable method of determining longitude at sea. The prize was eventually won by John Harrison, who built a clock accurate enough to maintain correct Greenwich time on a long ocean voyage. Harrison's achievement was partly mechanical and partly the arithmetic insight that longitude is, in a precise sense, a function of time difference. The great age of European exploration, the circumnavigation of Africa and the Americas, the establishment of global trade routes, all of it depended on sailors who could do arithmetic accurately under difficult conditions with instruments of limited precision. The entire colonial project, for better and for worse, was organized and made possible by arithmetic applied to navigation. Measurement and building brought arithmetic into engineering with a directness that has been with us since the first permanent structures. The Great Pyramid is aligned to true north with an accuracy of about 0.04 of a degree, which required sophisticated astronomical observation combined with careful arithmetic calculation. The Roman aqueduct system supplied cities with millions of liters of water per day, requiring gradients precise enough that water would flow by gravity over distances of tens of kilometers. Gothic cathedrals, with their soaring stone vaults and flying buttresses, represent solutions to structural problems. The forces of weight and thrust, calculated not with modern differential equations, but with the geometric and proportional arithmetic of medieval master builders. Modern structural engineering is more formalized, but draws on the same foundation. Load calculations for a bridge require knowing the weight of the structure, the expected traffic load, the dynamic forces from wind and vibration, and the properties of the materials, all combined through arithmetic and calculus to determine whether any component will fail. When a bridge fails, it is often because some arithmetic was wrong, either in the original design or in the assumptions about how materials would behave over time. Astronomy has always been intertwined with arithmetic, to the point where the two were nearly inseparable for most of history. The Babylonians developed their most sophisticated mathematics in service of astronomical prediction. The Islamic astronomers of the 9th through 13th centuries produced astronomical tables of remarkable accuracy by combining Greek theory with Indian arithmetic and their own extensive observational programs. Al-Battani, working in the 9th century, calculated the length of the solar year with an error of less than 3 minutes. Copernicus used arithmetic to argue that a sun-centered model fit the observed planetary positions better than the Earth-centered model. Kepler used arithmetic to discover that planets move in ellipses. Newton used arithmetic and the calculus he invented to prove that all of Kepler's laws followed from a single force law governing gravity. The precision of modern astronomy is arithmetic pushed to its limits. The positions of the Voyager spacecraft, launched in 1977 and now in interstellar space, are tracked by measuring the Doppler shift of radio signals and applying arithmetic to convert frequency shifts to distances and velocities. The predictions made when Voyager was launched about where it would be decades later, using only arithmetic and the known laws of planetary motion, were accurate to within a few hundred kilometers over journeys of billions of kilometers. That is, arithmetic as a precision instrument. Medicine has become arithmetically intensive in ways that would have been unrecognizable even 50 years ago. Drug dosages are calculated based on body weight and the pharmacokinetics of the drug. Getting them wrong can kill someone. Nurses and pharmacists who work with medication dosing are doing arithmetic under pressure, and medication errors from calculation mistakes are a genuine patient safety issue, not an abstract concern, a real one. Diagnostic imaging relies on arithmetic at a fundamental level. A CT scanner measures X-ray attenuation from hundreds of different angles around the body and uses a method called filtered back projection, which is arithmetic applied to the data from every angle to reconstruct a three-dimensional image of the body's interior. An MRI scanner measures the response of hydrogen atoms to magnetic fields and uses a mathematical transformation called the Fourier transform, which is arithmetic applied to the signal data to convert those measurements into an image of soft tissue. Without arithmetic, medical imaging does not exist. Climate science is arithmetic at a scale that is genuinely staggering. A global climate model divides the atmosphere, ocean, and land surface into millions of cells, and for each cell, at each time step, calculates the movement of heat and mass between adjacent cells using equations that encode the physics of fluid flow, radiation, and chemistry. Running one such model for 100 simulated years might require trillions of arithmetic operations. The results are not predictions of what will happen at a specific place and time, but projections of the statistical behavior of the climate system. The uncertainty in those projections comes from the uncertainty in the initial conditions and the simplifications in the model, not from arithmetic errors in the computation. The entire digital world runs on arithmetic. At the hardware level, a computer is a machine that performs arithmetic operations on strings of binary digits at billions of operations per second. The numbers inside a computer are stored as powers of 2, ones and zeros, base 2 rather than base 10. Binary arithmetic, with carries that happen at 2 rather than 10, is the native language of every processor ever made. Every program you have ever run is ultimately a sequence of arithmetic operations on binary numbers. Every image on a screen is a grid of pixels, each pixel defined by 3 numbers representing red, green, and blue intensity, each a binary integer that gets manipulated arithmetically whenever the image is transformed, filtered, composited, or compressed. Every song you have ever heard on a digital device is a sequence of numbers representing air pressure at moments in time, converted to sound by arithmetic on those numbers at 44,000 samples per second. The internet is packets of numbers transmitted between computers and reassembled at the destination. Every packet has a header with source and destination addresses, sequence numbers, and error-checking codes, all of which are arithmetic. The reliability of the internet rests on arithmetic verification. Artificial intelligence is, at its deepest layer, arithmetic. A neural network processes an input by multiplying it by a matrix of weights, adding a bias vector, and passing the result through a nonlinear function, then repeating this sequence through many layers. Training the network means adjusting those weights using gradient descent, which requires computing derivatives and updating weights in directions that reduce error. Computing those derivatives for a network with billions of parameters requires an enormous amount of arithmetic organized by the backpropagation algorithm. The output of a large language model generating text is the result of billions of such operations applied in sequence to the input. But the application of arithmetic in computing that has had the most direct and pervasive impact on ordinary life is probably cryptography. The security of nearly every private communication you have ever sent, every online purchase you have ever made, every password you have ever typed on a website, rests on a property of arithmetic that is simple to state. Multiplication is easy, but factoring is hard. Take two large prime numbers, each one a few hundred digits long, and multiply them together. That multiplication takes a fraction of a second, even on an ordinary computer. Now give someone the product and ask them to find which two primes were multiplied to produce it. That problem, for numbers of the size used in practice, takes longer than the current age of the universe with any known algorithm running on any existing classical computer. The operation that produces the product is computationally trivial. Inverting it is computationally infeasible. This asymmetry is the security of modern cryptography. RSA encryption, developed by Ron Rivest, Adi Shamir, and Leonard Adelman in 1977, uses this asymmetry as the basis for a public key cryptographic system. You choose two large primes, multiply them to get a public modulus, and publish that modulus along with a public exponent. Anyone who wants to send you a message encrypts it by raising the message, treated as a number, to the public exponent modulo, the public modulus. The result is a scrambled number that can only be unscrambled by someone who knows the private key derived from the two prime factors. Since nobody can efficiently find those factors from the public modulus, nobody can compute the private key, and the message stays secret. The arithmetic at the center of RSA is modular arithmetic, which deserves its own explanation because it is one of the most useful and underappreciated parts of arithmetic. Modular arithmetic is arithmetic with remainders. You pick a modulus, some fixed number, and instead of tracking the exact value of every calculation, you only track what the result is, modulo that number. In arithmetic modulo 7, 6 plus 3 equals 2, because 6 plus 3 is 9, and 9 divided by 7 leaves a remainder of 2. In arithmetic modulo 12, 10 plus 5 equals 3, because 15 divided by 12 leaves a remainder of 3. You know modular arithmetic already. It is how clocks work. 10 o'clock plus 5 hours is 3 o'clock, not 15 o'clock, because time on a 12-hour clock is arithmetic modulo 12. Modular arithmetic inherits the commutativity, associativity, and distributivity of ordinary arithmetic. You can add, subtract, and multiply modulo any number, and the results are consistent. Exponentiation works too. You can raise a number to a large power modulo, some modulus, efficiently using fast exponentiation, which repeatedly squares and multiplies. This is how RSA encryption and decryption are computed in practice. There is a theorem in modular arithmetic, proved by Euler and closely related to an earlier result of Fermat, that is the mathematical heart of RSA. Euler's theorem says that for any number a sharing no common factor with the modulus n, a raised to the power of the totient of n, all taken modulo n equals 1. The totient of n counts how many numbers less than n share no common factor with it. For the RSA modulus, which is the product of two primes, p and q, the totient is simply p minus 1 times q minus 1. This theorem guarantees that encryption and decryption are inverses. Encrypting and then decrypting returns the original message. The security of the modern internet is a direct application of a property of prime numbers that Euclid would have recognized, deployed through arithmetic operations that Brahmagupta would have used, protected by a theorem that Euler proved in the 18th century. When your browser connects to your bank's website and the padlock icon appears, you are using a chain of arithmetic reasoning that stretches back more than 2,000 years, and cryptography goes further than RSA. Elliptic curve cryptography, which has largely replaced RSA in many applications because it achieves comparable security with much smaller key sizes, is based on the arithmetic of points on elliptic curves described by equations of the form y squared equals x cubed plus ax plus b. Adding 2 points on an elliptic curve is a geometric operation that translates into arithmetic, and the resulting structure has properties that make it useful for cryptography. The discrete logarithm problem on elliptic curves, finding the integer n such that adding a point to itself n times gives another specified point, is computationally hard in a way that resists known attacks. That hardness is what secures billions of encrypted connections every day. Now, let's look at some of the deepest territory that arithmetic opens up, because the subject does not stop at applications. It reaches into questions about the nature of mathematics itself. In 1931, a 25-year-old Austrian mathematician named Kurt Gödel proved 2 theorems that permanently changed the way mathematicians and philosophers think about what mathematics is. The first incompleteness theorem says, roughly, any arithmetic system powerful enough to do ordinary number theory will contain statements that are true, but that cannot be proved within that system. You can add new axioms, new starting assumptions, and prove those statements, but then you will have new unprovable truths. You can never achieve completeness. There will always be arithmetic truths that your system cannot reach, no matter how carefully you build it or how many axioms you add. The second incompleteness theorem says, any such system cannot prove its own consistency. You cannot use arithmetic to prove that arithmetic is contradiction-free without already assuming something at least as powerful as arithmetic itself. The system cannot bootstrap its own reliability. These results were shocking. Mathematics had spent the previous decades, under the influence of David Hilbert's program, trying to build a complete, consistent, fully formalized foundation for all of mathematics. The dream was that you could write down a finite set of axioms and rules, and then every mathematical truth would follow from those axioms by mechanical, logical deduction. Gödel showed that this dream is impossible, not because mathematicians are not clever enough, because the structure of sufficiently expressive formal systems makes it unavoidable that some truths escape any fixed proof system. The way Gödel constructed his proof is itself a piece of arithmetic reasoning. He showed how to encode statements about arithmetic as numbers, so that the relationship of proving is reflected in arithmetic operations on those numbers. Then, he constructed a statement that, when decoded, says, essentially, this statement cannot be proved in this system. If the system is consistent, the statement is true, because if it could be proved, the system would be proving a falsehood. The statement says it cannot be proved, so the system cannot prove it, and the statement is therefore true but unprovable. What this means for arithmetic specifically is that the integers, despite being generated by the simplest possible rules, harbor an endless supply of facts that require stepping outside any given system to prove. The number line is richer than any finite description of it can capture. There are also natural mathematical statements that turn out to be independent of standard arithmetic axioms, not in the weird self-referential way of the Gödel statement, but in an ordinary-looking mathematical way. The Paris-Harrington theorem, proved in 1977, is a combinatorial statement about arithmetic. It says that a certain game played with numbers always terminates. The statement is true. It can be proved using a stronger system than ordinary arithmetic, but it cannot be proved within ordinary first-order piano arithmetic, the standard axiom system for the natural numbers. The statement is about everyday arithmetic objects, but requires stepping outside everyday arithmetic to prove. This phenomenon of natural arithmetic statements that cannot be proved within arithmetic itself suggests that Gödel's result is not just a curiosity about artificially constructed self-referential statements. It is a feature of arithmetic that shows up organically. The Riemann hypothesis might be in this category. We do not know whether the standard tools of mathematics are sufficient to prove it, or whether a proof would require new axioms. Now let's look at where arithmetic is going, because the subject is not static and several forces are currently reshaping it in ways that will matter. Quantum computers, if they can be built at scale, would break RSA encryption. Shor's algorithm, developed by mathematician Peter Shor in 1994, shows that a sufficiently powerful quantum computer could factor large numbers efficiently in time that grows as a polynomial of the size of the number rather than exponentially. Quantum computers are not classical computers. They exploit quantum superposition and interference to explore multiple computational paths simultaneously, and that gives them access to algorithms that have no classical counterpart. Shor's algorithm has been demonstrated on small-scale quantum computers. The challenge is scaling. Quantum systems are fragile, prone to errors from environmental interference, and maintaining enough stable quantum bits to run Shor's algorithm on cryptographically relevant numbers, which are typically 2000 bits or larger, requires error correction at a scale that has not yet been achieved. Building a fault-tolerant quantum computer capable of breaking RSA 2000 would require millions of physical qubits compared to the thousands that current machines have. The cryptographic community is not waiting to find out if that threshold is crossed. Post-quantum cryptography is an active field, and in 2022, the National Institute of Standards and Technology selected 4 post-quantum cryptographic algorithms for standardization. The most prominent of these are based on the hardness of problems in lattice mathematics. Given a lattice in high-dimensional space, find the shortest vector or find the lattice point closest to a given target. These problems have been studied extensively and show no sign of efficient quantum algorithms. The arithmetic underlying them is different from the modular exponentiation of RSA, but no less dependent on deep properties of numbers. The transition to post-quantum cryptography will be one of the largest infrastructure upgrades in the history of computing. Every system that currently uses RSA or elliptic curve cryptography will need to be upgraded. The arithmetic at the center of internet security will change, but the dependence of security on arithmetic properties of numbers will not. Machine learning has a different relationship with arithmetic, and it is starting to pull arithmetic in new directions. Neural networks are arithmetic machines. Their operation is matrix multiplication and addition, repeated and composed. Their training is arithmetic optimization. The models that currently perform the most impressive tasks in language, image generation, code writing, and scientific modeling are, at their computational foundation, incredibly fast and incredibly large arithmetic systems. What is new is that these systems are being turned back toward mathematics itself. The lean proof assistant and similar formal verification systems allow mathematical proofs to be checked by computer, and AI systems are being trained to generate and verify formal proofs. In 2023 and 2024, AI systems made concrete progress on problems in combinatorics and representation theory, finding solutions to problems that had stumped human researchers. DeepMind systems found new algorithms for matrix multiplication that are more efficient than the best-known human-designed algorithms by searching a space that is too large for humans to explore manually. The question of whether an AI system could contribute to the Riemann hypothesis, or to Goldbach's conjecture, or to the twin prime problem is no longer obviously beyond reach. These are hard problems. The specific kind of mathematical creativity they require, finding genuinely new ideas rather than searching through known combinatorial space, may be beyond current systems. But the trajectory of the tools is clear. What makes arithmetic a particularly good domain for this kind of collaboration is that arithmetic has a hard notion of truth. A proof is correct or it is not. A counterexample either exists or it does not. There is no ambiguity about whether an arithmetic claim is correct once it has been fully checked. This makes it possible to build systems that verify arithmetic reasoning reliably, in a way that is much harder to achieve in domains where correctness is contextual or a matter of judgment. There is a question that sits beneath all of this, quiet but persistent, that the history of arithmetic keeps returning to in different forms. Why does arithmetic describe the physical world? The numbers we use to count objects, the operations we use to combine quantities, the prime numbers that emerge from the structure of the integers. All of these were developed entirely within human minds, thinking about abstract structures. Nobody sat down with a particle accelerator to develop number theory. And yet, prime numbers show up in the life cycles of periodical cicadas, 17-year cicadas, and 13-year cicadas, species that spend almost their entire lives underground and emerge only to breed. The cycle lengths are prime. The leading hypothesis is that this is an evolutionary adaptation. Prime length cycles are harder for predators to synchronize with than composite length cycles, because a predator with a cycle of any length that divides into 17 or 13 would have to wait the full 17 or 13 years for their peak populations to coincide. The arithmetic property of primeness, worked out by human mathematicians in the abstract, was apparently worked out independently by evolution and encoded in the biology of insects. Modular arithmetic describes the symmetries of physical crystals. The allowed arrangements of atoms in a crystal are constrained by group theory, which is built on modular arithmetic. The Fibonacci sequence, generated by a simple arithmetic recursion, where each term is the sum of the previous two, appears in the spiral arrangements of sunflower seeds, pinecone scales, and nautilus shells, in patterns that minimize packing density and allow for efficient growth. The irrational number E governs radioactive decay, where the amount of a radioactive substance decreases by a factor of E for every mean lifetime that passes. The same number governs population growth under certain conditions, compound interest in the limit of continuous compounding, and the statistical distribution of the gaps between consecutive prime numbers. The physicist Eugene Wigner wrote in 1960 about what he called the unreasonable effectiveness of mathematics. He was noting that mathematics, invented with no physical application in mind, sometimes centuries before any application emerged, repeatedly and accurately describes physical reality. Complex numbers, invented to handle the square roots of negative numbers, turned out to be the natural and unavoidable language for quantum mechanics. Quantum mechanics requires complex probability amplitudes. Using only real numbers produces a theory that does not match observation. The Riemann zeta function, a piece of pure number theory, turns out to describe the energy levels of certain quantum chaotic systems in a precise statistical sense. Group theory, developed in the 19th century to understand the symmetries of polynomial equations, describes the fundamental particles of physics. Every known particle corresponds to a representation of some symmetry group. Why this happens is genuinely open. There are several positions people take. One says mathematics is invented, a human construction, and its effectiveness is explained by evolution. We evolved to reason about patterns in the physical world, and mathematics is a refined version of that pattern recognition. Another says mathematics is discovered, not invented, that the integers and their properties exist independently of any mind that thinks about them, and that what we call doing mathematics is exploration of a territory that was always there. Max Tegmark has argued for the most extreme form of this view, that the physical universe is not just described by mathematics, but constituted by it. There is no separation between the map and the territory. Under this view, arithmetic's effectiveness at describing physics is explained by physics being arithmetic. A third position says the question might be malformed. We select the mathematical tools that work and forget the ones that do not. The mathematics that did not describe reality gets abandoned or ignored, and we are left with a biased sample of mathematical theories that happen to match physical reality. The unreasonable effectiveness might be a selection bias. None of these positions fully closes the question. And that open question leads directly into what comes next, because where arithmetic goes from here is tied up with how well we understand what it is in the first place. Several predictions feel grounded in current trajectories. Post-quantum cryptography will become the global standard within the next 10 to 15 years. The transition has already started. NIST published its first post-quantum standards in 2024, and major software systems are already beginning to incorporate them. The arithmetic at the center of internet security will be lattice-based rather than factoring-based, requiring users and developers to trust different mathematical assumptions. For most people, this transition will be invisible. The padlock in your browser will still appear, but underneath, the arithmetic will have changed, and the 2,000-year chain of number theory connecting Euclid to your bank account will have grown a new link. A machine-assisted proof of a significant open conjecture, not the Riemann hypothesis, but something in combinatorics, graph theory, or finite group theory, will be announced within the next decade. The tools exist. Lean and other formal proof assistants, large language models that can generate and check proofs, high-performance computing that can search combinatorial spaces. The remaining gap is in generating genuinely novel mathematical ideas rather than checking and combining known ones. That gap is narrowing. When the first machine-assisted proof of a major conjecture is announced, it will raise a question that arithmetic cannot answer for itself. What counts as understanding? A proof that no human can hold in their head at once, generated with machine assistance, is still a valid proof. But it will feel different from the kind of understanding Euclid had when he proved that the primes are infinite. The educational approach to arithmetic will undergo significant changes as AI-based tutoring systems improve. The experience of learning arithmetic has been fundamentally unchanged for over a century. A teacher explains a procedure, students practice it through repetition, mistakes are corrected, the next procedure is taught. AI tutoring systems can adapt to each student's current understanding, identify specific misconceptions, and provide targeted practice at the right level of difficulty in real time. Whether this improves arithmetic education in practice, or whether it displaces the development of procedural fluency that underlies more advanced mathematical thinking, is an open empirical question. The evidence suggests both matter. You need to know why the operation works and be able to execute it reliably, and the two forms of knowledge reinforce each other. The Riemann hypothesis will probably be resolved in this century, though the method that resolves it is impossible to predict. The most plausible path, based on current mathematical progress, involves a deeper connection between the zeta function and the spectral theory of certain operators, a connection suggested by parallels between the distribution of zeta zeros and the distribution of energy levels in quantum chaotic systems. This correspondence, discovered in the 1970s by Montgomery and Dyson and studied intensively since, might eventually lead to a physical system whose properties encode the Riemann hypothesis, and proving that the system has those properties might be more tractable than attacking the hypothesis directly. But this is speculation. Mathematical progress is not linear, and the resolution, if it comes, might come from a direction nobody has thought of yet. It might come from a person nobody has heard of yet. That baboon bone, with its 20,000-year-old notches, is still in Brussels. The person who carved it, and we do not know if they were a man or a woman, young or old, whether they were keeping track of something practical or exploring something abstract for its own sake, had a brain not very different from yours, the same neurons, the same basic wiring for number sense, the same capacity to look at a quantity and want to hold it still, to mark it, to do something with it. Between them and you, a very long chain of people added things to arithmetic. Sumerian scribes counting grain and pressing receipts into wet clay. Babylonian scribes calculating compound interest 4,000 years before modern banks. Egyptian scribes working out how to cut pyramids to the right proportions. Greek philosophers arguing about whether numbers were invented or discovered, whether irrationals were numbers at all, whether infinity could be actual or only potential. Indian mathematicians sitting with the philosophy of emptiness long enough to decide that nothing was a number. A Persian scholar in Baghdad writing down the step-by-step procedures for decimal arithmetic and inadvertently naming the concept of algorithm. An Italian merchant's son who spent his childhood in North Africa and came back to Europe knowing that he had seen a better way to count. A Scottish nobleman who spent 20 years devising a way to turn multiplication into addition and saved countless navigators from shipwreck. A German mathematician staring at a function in the complex plane and writing down a conjecture he could not prove that nobody has proved in 160 years. A young Austrian who showed that no system of arithmetic can know everything about itself. And on the other side of all that, every online purchase, every encrypted message, every medical scan, every climate model, every video stream, every GPS coordinate, every algorithm running on every device, every piece of software ever written, every number you have ever read on a screen. Arithmetic started with a bone and some notches carved in the dark, before language, before writing, before anything that looks like civilization. It spread around the world through trade routes and religious centers and translation projects and the slow grinding pressure of practical need. It accumulated properties and theorems and applications and open questions until it became the foundation beneath all the rest of mathematics and most of the modern world. And it is still going. The bone in Brussels is 43,000 years old if you count the Le Bombo bone, and the primes are still scattered out there in all their strange regularity, and the full story of why they are distributed the way they are has not yet been written. What the next person who closes that gap will look like, what tools they will have, whether they will be human or human-assisted, or something we do not have a word for yet, is unknown. But the gap is still there, the question is still open, and the counting is still going.